The Gaussian wave packet consists of the wave function psi of x comma 0 given by a times e to the minus small a x squared. So the first thing we need to find is we need to normalize normalize the wave function. Then we're gonna have to find the wave function in terms of x and t. Then we need to find, we need to find psi star psi, or the module square of psi. A, B, C, D. We need to find the expectation value of x, the expectation value of the momentum, the expectation value of position square, and the expectation value of the momentum square. Also, we need to find the uncertainty in position and the uncertainty in momentum. So 4 parts, so let's get started. The first thing we need to do is normalize the wave function, right? So 1 is equal to the module square of a times the integral from negative infinity to infinity of e to the minus 2 a x squared dx, which is equal to a squared times the square root of pi divided by 2a. Solving for a, we have the normalization constant equals to the 4th root of 2a divided by pi. There you have it. This is the first part of the question. The second part, we need to find the wave function, right, in terms of position and time. So first thing we need to do is we need to find phi of k. Phi of k is given by equation number 6 in video number 16. So phi of k is equal to 1 divided by square root of 2 pi times the normalization constant a times the integral from negative infinity to infinity of e to the minus a x squared times e to the minus I k dx. Alright, so now we're gonna have to do a few things. So we have to let b, we're gonna define this variable b equals to ik. We're gonna have to find another variable y. We're gonna define it as square root of a times x plus b divided by 2a. And if we solve this equation, a x squared plus bx, this is going to be equal to y squared minus b squared divided by 4a. If you wonder why we're doing this, you're going to see in a minute. So now I can rewrite the above integral as 1 divided by square root of 2 pi times a times the integral from negative infinity to infinity of e to the minus a x squared plus bx, right, which is b is minus ik dx, and that's the same as 1 divided by square root of 2 pi times a times the integral from negative infinity to infinity of e to the minus y squared plus b squared divided by 4a times 1 divided by square root of a dy. This 1 divided by square root of a came from the dy. Okay, so now we're gonna carry on with the integral. So this is equal to 1 divided by square root of 2 pi times the normalization constant a times 1 divided by square root of a. I'm gonna factor this one out, times e to the b squared divided by 4a, this is also a constant, times the integral from negative infinity to infinity of e to the minus y squared dy. And this is equal to 1 divided by square root of 2 pi times a. Doing the integral and evaluating it, we get e to the b squared divided by 4a, and there's a constant in the front here, square root of pi over a. So now in terms of the k, we have phi of k finally equals to 1 divided by square root of 2 pi times the normalization constants, 2a divided by pi to the 1/4 power times square root of pi divided by a times e to the minus k squared divided by 4a. Simplifying a little bit further, we have 1 divided by 2 pi a to the 1/4 times e to the minus k squared over 4a. So this is our phi of k. Now we plug this back into the psi equation to find part c of the problem. So psi of x comma t is equal to 1 divided by square root of 2 pi, right, times 1 divided by 2 pi a to the 1/4 times the integral from negative infinity to infinity times e to the minus k squared over 4a times e to the I times k x minus h bar k over 2m times t dk. Does this look familiar here? So here we have k squared and k, so these are 3 terms, right? So this can be simplified as this is the same, this goes here the same, times the integral from negative infinity to infinity of e to the minus, open brackets, open parentheses, 1 divided by 4a plus I h bar t divided by 2m, this is times k squared, right, minus I x k dk. So this here, we evaluated this integral from part 2 of the problem. So this is equal to 1 divided by square root of 2 pi times 2 pi a to the 1/4, right, times square root of pi divided by square root of 1 over 4a plus I h bar divided by 2m times t right, okay, times e to the minus x squared divided by 4 times 1 over 4a plus I h bar divided by 2m times t. Let's simplify a little bit further. So psi of x comma t is finally equal to 2a divided by pi to the 1/4 times e to the minus a x squared divided by 1 plus 2 I h bar a divided by m times t all over square root of 1 plus 2 I h bar a over m times t. I would recommend you go through the algebra because there's a lot of steps going between this above equation and this boxed equation. So I skip a lot of algebra in between these steps. So this is our wave function in terms of position and time. C, we have to find psi star psi, right? So before we do this, let theta, I'm gonna define a new variable to make our life easier. Let theta be square root of a divided by, sorry, no. We can define theta to be 2 h bar a divided by m times t. So now we have psi star psi equals to square root of 2a over pi times e to the minus a x squared divided by 1 plus I theta times e to the minus a x squared divided by 1 minus I theta. As you see, theta is a dimensionless quantity, so it has no dimensions, right? That's why we define these variables, so we can make sense of the equation. Divided by 1 plus I theta times 1 minus I theta. Let's simplify it a little bit further, but before this, let's take a look at the exponent minus a x squared divided by 1 plus I theta minus a x squared divided by 1 minus I theta. This can be written as minus a x squared times 1 minus I theta plus 1 plus I theta divided by 1 plus I theta times 1 minus I theta, which is the same as, this can be written as 2 minus 2a x squared divided by 1 plus theta squared. Okay, so finally we have the modular square of psi is equal to square root of 2 pi divided by 2a divided by pi times e to the minus 2ax square divided by 1 plus theta square divided by square root of 1 plus theta square. Right? So now let's define a new variable so we can understand this quantity. So let's define omega as square root of a divided by 1 plus theta square. So with omega we have x psi star psi equals to square root of 2 over pi times omega times e to the minus 2 omega square x square. This looks like the harmonic oscillator, right? So let's plot this a little bit. So if we plot psi star psi, so this is x, this is psi star psi at t equal 0. This should look like, no, it's not a surprise, it's gonna look like a Gaussian. And as the time evolves, so t is positive, as time increases, psi star psi become very flattened. So become very flat. Okay, so now part D, we have to find the expectation value of x. Remember this, we have to sandwich x between psi star psi, so we have this psi star x times psi dx. This is equal to 0. Why? Because we have an odd integral. Odd integral. Okay, so the expectation value of P, momentum, this is mass times the time derivative of the expectation value of x, which is also 0. Let's carry on a little bit further. Now we need to find the expectation value of x squared, right? Which is, we have to sandwich x squared into our psi star psi, which gives us a square root of 2 divided by pi times omega times the integral from negative infinity to infinity of x squared e to the minus 2 omega squared x squared dx, which is the same as square root of 2 over pi times omega times 1 divided by 4 omega squared times the square root of pi divided by 2 omega squared. Simplifying a little bit further, we have expectation value of x squared equals 1 divided by 4 omega squared. Nice. So now we have to find the expectation value of p squared, and that is the same as minus h bar squared times the integral from negative infinity to infinity psi star times the second time derivative of what? Of psi dx. So first we need to find the second time derivative of psi, stick it into the integral and evaluate. So let's simplify stuff so we can solve this problem. Let's define b, some new variable b, as 2a divided by pi times to the 1/4 times 1 divided by square root of 1 plus I theta. Right? And let's define small b as a divided by 1 plus I theta. Okay, so now if we take the second derivative of x with the second derivative of psi with respect to x. I'm sorry, earlier I said this is t, it should be x. So this should be x. I can't write. Anyway, so this here should be x. Okay, so the second derivative of psi with respect to x is equal to, we're gonna factor out b outside, and if I take the first derivative, which is 2 minus 2 bx e to the minus bx squared, right? Taking another derivative, this gives us minus 2 b times big P times 1 minus 2p x squared times e to the minus p times x squared. Alright, so now psi star times the second derivative of psi with respect to x is equal minus 2 times b times module square of big P times 1 minus 2b x squared times e to the minus b plus b star times x squared. Right? Let's take a look at this quantity here. This one here. Let's take a look at this. So b plus b star is equal to a divided by 1 plus I theta, right? This is b, plus b star, which means just change the imaginary part to a minus. So this is equal to 2a divided by, we did this before, 1 plus theta squared. In terms of omega, this is exactly equal to 2 times omega squared. Right? And b star b is equal to square root of 2a over pi times 1 divided by square root of 1 plus theta squared. And in terms of omega, this is equal to square root of 2 divided by pi times omega. Alright, so let's go back to the original color. We have psi star times the second derivative of psi with respect to x equals to minus 2b times the square root of 2 divided by pi times omega times 1 minus 2b x squared times the exponential part, omega squared x squared. Alright, so almost done. So now the expectation value of the momentum square is equal to 2 times b times h bar square times the square root of 2 divided by pi times omega times the integral from negative infinity to infinity of 1 minus 2b x squared times e to the minus 2 omega square x square dx. As you see, this is two integrals, right? So let's carry on a little bit further. So this is equal to 2 minus 2, no, positive 2, b h bar square times the square root of 2 divided by pi times omega times square root of pi divided by 2 omega square minus 2 times b times 1 divided by 4 omega square times the square root of pi divided by 2 omega square. Simplifying a little bit further, we get 2 times b times h bar square times 1 minus b divided by 2 omega square. But we know that 1 minus b over 2 omega square is equal to 1 minus a divided by 1 plus I theta, right, times 1 plus theta square divided by 2a, right? Simplifying a little bit further, this is equal to 1 plus I theta divided by 2, which is the same as a divided by 2b, right? So finally, the expectation value of p square is equal to 2 times b times h bar square times a divided by 2 pi b, which is the same as h bar square times a. Alright, almost done. So now we have to find the uncertainty in x and the sigma of p. So sigma x, this is from earlier videos, is equal to 1 divided by 2 omega. And finally, sigma p is equal to h bar times the square root of a, right? So if we multiply the two to find the uncertainty principle, if it holds or not, so this is equal to 1 divided by 2 omega times h bar square root of a, which is the same as h bar divided by 2 times the square root of 1 plus 2 h bar a t divided by m square, which is definitely less than, greater than or equal to h bar over 2, right? Because this here, if this is 0, if this term is 0, then this is going to be h bar over 2, right? So this is going to be equal to h bar over 2. And if this is not 0, then this is going to be greater than that. So this is definitely satisfy the Heisenberg principle.